Okay, so this video will cover practice question 6 on probability. Uh, so the first question, what is the relevance of probability in inferential statistics for education research? I've already written the answer down. So we know in inferential statistics we have a population that we want to do, like we have some research question or hypothesis that we want to test on the population. Uh, this requires sampling out of the population. Usually we can't conduct uh, some analysis on the population, so we select the sample out of the population, and then based on our results on samples, then we make generalization to the population. This relationship from population to sample is described by probability, and the relationship from sample to the population is defined by inferential statistics. Okay, let's look at question 2. What are the two requirements for a random sample? So the first requirement is that each individual has the same probability of being selected. So each individual will have the P will be equal to 1 over n, which is the size of the population. So it means that everyone has the same 1 over n probability of being selected. And the next one is the selection should be by replacement. This is to basically make sure that we have constant probability. So this is to constant probability for each and every selection, basically. Okay. Okay, let's look at the next question. Define sampling with replacement and explain why it is used. So I'm gonna explain briefly. Selection by replacement is, I'll just explain it by like a dice. So like for example, we have a dice. We're like rolling a dice. This is like 1, 2, and then we have like 4 here. Anyway, it was unnecessary, but so imagine we want to roll the dice 3 times and see what we can sample from this dice. This will be the sample. So n equals, or basically n, because this is a sample, our sample is size 3. So we roll it once, we get 2. If it wasn't with replacement, imagine if you remove 2 from the sample. So we can't get 2 anymore. So the next time you roll, you can get 2, you get 1, for example. Like you roll the dice, you get 1, and the next time you can't again get 1 anymore. So you'll get 4 the next time. This is without replacement, meaning that once you roll two, you don't replace it again in the population for it to be selected again, which is obviously the wrong way to do the sampling. The right way would be to, once you roll two, you keep two again in the sample, so you have the chance to roll two times in your sample. Again, the better example would be a deck of cards. So we have a deck of cards. Uh, so imagine like you pick a card. What is the probability of picking, for example, like King of Spades or King of Hearts, for example? Like, what is the probability of that? Is 1 over 52 to pick that, right? Because we have 52 cards in the deck. But imagine if we do our first sample, it's not a King of Hearts. So for the next one, when we want to pick a card again, then the probability of picking a King of Hearts is 1 over 51. Why? It's because we already picked one card, threw it away, so we have now 51 cards. This will be if we don't replace the card that we picked and put it back in again. So this is the first situation when you've done it without replacement. With replacement, it would be as you pick a card, it is like, I don't know, like 8 of diamonds. Uh, and it's, imagine, yeah, it is like 8 of diamonds. Let me. But it wasn't the King of Hearts, basically. So you put the 8 of diamonds back in again, uh, you shuffle the cards, and you pick again. For the next one, the probability of picking King of Hearts is still 1 over 52. This ensures that the requirement that we had here that probability remains constant is actually met. So if we don't replace it, basically it changes the population and then the probability of being selected every time. Yeah. So we kind of talked about question 4 as well. So let's see. What is the risk involved in conducting random sampling without replacement? The risk is basically the probability of being selected will remain constant. Because we basically are changing the population. If we don't replace the ones that we've selected ones, so it will change the population and the probability will change. Uh, yeah. So, for example, if we don't replace, uh, the probability is 1 over n at first, and then the next time it'll be 1 over n minus 1. The next time will be n minus 2. But we want this probability to remain the same. So we do the replacement every time we pick something. we put it back in the selection pool, basically. Okay, let's look at question 4 or 5. Sorry. There are 9 pillows in a bed. 9 pillows, 3 are red, 5 are yellow, and 1 is blue. What is the probability of picking yellow? So let me write it down. We have 9 pillows, right? 3 red, 5 yellow, and 1 is blue. So 3, 5. 5 is yellow, 1 is blue, right? And we want the probability of picking a yellow pillow. So probability of picking yellow will be the 5/9, because we have 5 yellow pillows and 9 pillows in total. Or we can, the formula would be P equals F divided by N. So we know that F for yellow is 5 and N is 9. Okay, so question 6. 2 coins are tossed 500 times. So 2 coins 500 times. And we get 2 heads. So 2 heads is 105. 1 head 275, and then no head 120. So to do this, I'll usually make a table. This side is coin 1, this side is coin 2. So this part is head, this is tail, this is head, this is tail. So we had 2 heads, so here is having 2 heads. We have this 105 times. We had 1 head, so it means that 1 head is basically when coin 2 is head and coin 1 is tail. So here, basically this cell, and also coin 1 being head and coin 2 being tail is also 1 head. So here's another one. These two, let me call them. So if this is A, this is, let me remove this. This is A, this is B. A plus B equals 275. And then we had no head 120 times. So no head will be both coins being tail. So here, basically. So we know C is 120. And then let's call this D. So we know also D is 105. So what is the question. Find the probability of each event to occur. So first, the probability of having two heads will be 105 divided by 500. Let me write this. So P of, and we call this, let's see, this is event A, this is event B, this is event C. So P of event A equals F divided by N. F we have is 105, N is 500. Let's simplify this. So this divided by 5 is 21 over 100, which is equals to 0.21. P of B, which is having one head, is F divided by N, and then F we know is 275 divided by 500. Let's see, this will be believe it will be 55 over 100, which will be 0.55. Let me double check this really quick. 275 divided by 500, yes. And then probability of event C, which will be having no head, as 120 divided by 500, which will be 24 divided by 100, which is equals to 0.24. And then, so this is probability of each event, and then check or verify if the proportions add up to 1. So let's see, PA plus PB plus PC will be 0.21 plus 0.55 plus 0.24. This is equal to 24 plus 21 equals 0.45 plus 0.55, which is equals to 1. And it also makes sense because it covers all the probabilities, because basically PA was year, PB was these two, and PC was here. So we can see it covers all of the cells or all of the possible outcomes. Okay, question 7. The psychology class consists of 32 freshmen, so 32 freshmen, 48 sophomores. So if the professor select names from the class list using random sampling, what is the probability that the first student selected will be a freshman? So P of selecting freshman, we define event A as selecting a freshman. So P of A equals to F divided by N. So F we know is 32, and then N is 32 plus 48. This is 32 divided by 80. which is equal to 0.4. And then question B is, and if a random sample of n equals 6 students selected and the first 5 selected are sophomores, so we have n equals 6 samples. We know first 5 are sophomores. What is the probability that the 6th student selected will be a freshman? Since we know that, basically going back to question 2, we know that selection first should be by replacement, and then the probability for each and every selection should be constant, and then basically the selections are independent from each other. This means that no matter if the first 5 are sophomores, the probability of picking the 6th student should be, or the probability should remain constant through selection. And therefore, for the last one in the sample, the probability will still be the same as selecting a freshman as we looked at in part A. So the probability will still be 0.4. Okay, so that was question 7. Question 8. Give me a second. Let me pull this up somewhere else so I don't have to scroll every time. Okay, so for question 8, okay, 8. So for 8, we have bag of Skittles candies include 6 different colors. So 6 colors, which is red, orange, yellow, green, blue, yellow, green, blue, and purple. Okay. If the bag has an equal number of each of the 6 colors, what are the probabilities for each of the following? So we know that these have the same number of candies. Let's consider the number as K. So we have K red candies, K orange, K yellow, K green, K blue, and K purple. So K is just a number, like 5, 5, 6, whatever. So what is the probability of selecting a green candy? So P of green is equals to F divided by N. So we know that F for green is K. and n is n times k. No, I'm sorry. I meant 6 times k, because we have 6 colors, each of them have k candies, which will be 1 over 6. Or basically, the easier way to say is that if we have equal number of candies for each color, it doesn't matter how many of each we have, because they are all the same number. The probability will be 1 over 6, as if we had one candy from each color. So 2 is randomly selecting either a green or a yellow. So P of green or yellow will be, again, F over N. So F will be green or yellow, so will be K for green and K for yellow. This is the F for green and yellow. And then N will be, again, 6 times K, so it will be 2K divided by 6K, which is 1 over 3. And then for 3, randomly selecting something other than a green candy. So there are 2 ways to do it. First, we can say that P, let's call this event A. So event A, let me write this again. A is picking something other than green. So one way is to PA to be equal to F divided by N. So this F will be all the other colors except green. So this will be 5K, because we have 5 other colors, and K is the frequency of each of those, and then divided by 6K, which will be 5 over 6. Another way is that P of A is 1 minus P of picking green, which will be 1 minus 1, 6, which again is 5 over 6. Let me what this could mean is that basically the probability of picking green is the same as probability of like the sum of all probabilities minus probability of getting green. So because 1 is basically the sum of all probabilities here, so we basically subtract probability of picking green from the sum of all the other possible situations. Because here it was easy to kind of figure out this 5K over 6K, which is the sum of all the possible probabilities, but sometimes it's not that straightforward. So sometimes it's easier to kind of find the probability of things that we don't want to see, and then subtract that from every other possible condition. So that is question 8. Question 9 is, a jar contains 30 red marbles and 4 blue marbles. If one marble is selected from the jar, what is the probability that the marble will be red? The probability of red will be F over N, We know F is 30 red marbles, and then N is 30 red marbles and 40 blue marbles. So this will be 30 over 70 or 3 over 7. And then question 10. If two coins are tossed simultaneously, what is the probability of getting exactly two heads? So this is again the same or not the same, or similar to this coin question that we had. I'll make the table again, more like a grid. So this is our coin. This is coin 1, and this is coin 2. This is coin 1 head, tail. This is head again. This is tail. So basically we know that for each coin we have 50-50, basically equal probability of getting head or tail. So in this situation we have 0.25 for both being head, 0.25 for coin 1 being head and coin 2 being tail. We have 0.25 for coin 1 being tail, coin 2 being head, and then we have 0.25 for coin 1 being tail and coin 2 being tail. Or we can kind of write it this way. So if we have two independent events, the probability of A and B happening is equal to probability of A times probability of B. So we can also solve that this way. So probability of getting two heads. So here A is coin 1 head, B is coin 2 head, or we can change it around, doesn't matter. And we know that these are independent events. The event of basically tossing the first coin is independent from tossing the second coin. They don't impact or influence each other in any way. That's why we call them independent. So probability of two heads will be P of A times PB. So PA we know is 0.5, then PB is 0.5. So the probability of two heads is 0.25. Okay, that's all for practice question 6.